In these problems, we will take a series of phase change type problems where we'll have a substance that's provided to us and it may go through multiple changes in state. So let's take this problem. 85, a substance X has the following properties. And so here notice you have heat of vaporization, heat of fusion provided, as well as the boiling point, the melting point, and a series of heat capacities in the solid, liquid, and gaseous state for the substance. Now it asks you to sketch a heating curve. We're going to ignore this part and move on to 86, where given the data in exercise 85, on substance X, calculate the energy that must be removed to convert 250 grams of substance X from a gas at 100 degrees Celsius to a solid at negative 50 degrees Celsius. Assume X has a molar mass of 75 grams per mole. So the most important aspect of this problem is that you write out in this kind of note formation the changes in state, because there's going to be 5 different possible calculations for these type of problems. We'll have that is a heat either absorbed or released in the gaseous state, the change going from gas to liquid or liquid to gas, the heat absorbed or released in the liquid state, the heat change either going from liquid to solid or solid to liquid, and finally heat absorbed or released in the solid state. So it's always important to just map out distinctly the state you're beginning in and the temperature. So we're beginning with a gas at 100 degrees Celsius, and of course the boiling point is 75 degrees Celsius. So I'm going to say we're going to go from the gas at 100 degrees Celsius to the gas state at 75 degrees Celsius. Now, at that boiling point, there is a phase change in which the gas at 75 degrees Celsius will become a liquid at 75 degrees Celsius. And then we continue from there. Now that we're in the liquid state, we're going to go from liquid at 75 degrees Celsius to liquid at negative 17 degrees Celsius. That's because the melting point is at negative 15 degrees Celsius. So then we'll transition liquid at negative 15 degrees Celsius to solid at negative 15 degrees Celsius. And we're told finally that this is going to end up as a solid at negative 50 degrees Celsius. So we'll go from solid at negative 15 degrees Celsius to solid at negative 50 degrees Celsius. So this right here is the most important part for this type of problem. Now, for just heat changes in a certain state, we will use Q is equal to MC delta T. So that's for gas, for liquid, and for solid. But when we have a phase change, we will use either the heat of vaporization, of course, for when we're either going from gas to liquid or liquid to gas, and heat of fusion when either we're going from liquid to solid or solid to liquid. So let's begin with the first calculation. Q is equal to MC delta T. We will use the mass given to us, 250 grams, and the heat capacity of the gas. So notice here, the heat capacity of the gas is 1 joule for every gram being raised 1 degree Celsius. So this is the heat capacity of the gas. And then we're going to provide our change in temperature, our delta T. And change is always final minus initial. So always final, 75 here, minus 100. And so it's important that we preserve that delta, because that's going to be a negative change. And what that will convey is that heat is being removed. Of course, we're going from 100 to 75. Heat must be removed from our system. I would also urge you to convert directly to kilojoules, because your heat of vaporization and heat of fusion are already in kilojoules, and that will make your calculations easier if you just convert to kilojoules right here as well. And so that will be negative 6.25 kilojoules. Also, what's important to note for significant figures, if you notice, we've got 2 significant figures as the least number in our multiplication. Underline that, because it's going to be important when we add all of these values together at the end. So the next calculation, notice I have negative delta H vaporization. That's because we are not vaporizing. We're not going from liquid to gas. We're going from gas to liquid. So we're doing the reverse process here. So that's negative delta H. And so since delta H is 20 kilojoules per mole for the heat of vaporization, that's going to be negative of that value times the number of moles. And of course, I did that calculation up over here because it's just convenient to do, and then just substitute for moles. So the moles would be the mass, right, divided by the molar mass that's provided to us. And they told us, assume X has a molar mass of 75 grams per mole. So we have that right there. And that will be negative 66.6 kilojoules released. The negative sign is implying release, of course. So next calculation, in the liquid state, the mass 250 grams times the heat capacity of the liquid. Heat capacity of the liquid 2.5 joules per gram degree Celsius. And of course the change, negative 15 minus 75, negative 90 degrees Celsius. And again, converting to kilojoules, that's negative 56.25 kilojoules. The next calculation, again, the change in H associated with the process of fusion, but fusion is going from solid to liquid. And since we're doing the reverse process, we're going to apply a negative sign here, so negative delta H of fusion. And so we have negative 5 kilojoules per mole. Then being multiplied by the number of moles, we get negative 16.6 kilojoules. And finally, our last calculation, using MC delta T, the mass, again, 250 grams, times the heat capacity of the solid, times the change in temperature, since negative 50 minus negative 15 gives us negative 35, and then converting to kilojoules, negative 26.25 kilojoules. So the last part is to add all of these values together, and here we get negative 172.08, and I'm using the other rule for significant figures that when you add, right, you will round to the least number of decimal places. And so since this value and this value and this value and this value would have been rounded to the ones place, we will round this to the ones place as well. So this is negative 172 kilojoules. So 172 kilojoules of energy would have to be released or removed from this system in order to go from the gas, that substance in the gaseous state at 100 degrees Celsius, to that substance in the solid state at negative 50 degrees Celsius. So the next series of problems are going to be quite similar. Again, so how much energy does it take to convert 0.5 kilograms of ice at negative 20 degrees Celsius to steam at 250 degrees Celsius? So now we're working with water, and they're giving us the heat capacities of ice, liquid water, and steam, as well as the heat of vaporization and the heat of fusion. And they assume that you already know that the melting point for water is 0 degrees Celsius and the boiling point is 100 degrees Celsius. Again, the most important thing is to plot out the changes. So solid at negative 20 degrees Celsius will be turned to solid at 0 degrees Celsius, and then we'll go from solid at 0 degrees Celsius to liquid at 0 degrees Celsius, liquid at 0 degrees Celsius to liquid at 100 degrees Celsius, liquid at 100 degrees Celsius to gas at 100 degrees Celsius, and finally gas at 100 degrees Celsius to gas at 250 degrees Celsius. The calculations are going to essentially be very similar. Of course, the major difference here is that we're absorbing energy here. So all of your heat will be positive, right? And of course, you will have a different mass that we're working with. I would urge you to convert that to grams since your heat capacities are in per gram. So of course, 0.5 kilogram, that's just going to be 500 grams. So make sure you have your appropriate units, and then at the end, you'll add all those values together, and that will be the heat energy that is required, the heat energy that must be absorbed in order to convert that much ice at negative 20 to steam at 250 degrees Celsius. Here's another type of problem where it's, again, very similar. Consider a 75-gram sample of water, gas, in the gaseous state at 125 degrees Celsius. What phase or phases are present when 215 kilojoules of energy is removed from this sample. So again, here, essentially, they're giving you the amount of energy, and really what you should do is just do a step-by-step calculation. Go from the gas at 125 degrees Celsius to gas at 100 degrees Celsius and calculate that heat energy that must be released, right? And if it's less than this value, then go on to the next calculation. So gas at 100 degrees Celsius to liquid at 100 degrees Celsius, calculate that using the heat of vaporization or negative heat of vaporization, then add that to this value. If that's still less than this, then you have to go on to the next calculation. And so essentially, once you get over this value, then you know where you kind of fit in between, right? So if we do this conversion, right, and calculate this heat energy, and it's over this, then we can clearly say that the substance will be in the liquid state. Next problem, an ice cube tray contains enough water at 22 degrees Celsius to make 18 ice cubes that each have a mass of 30 grams. The tray is placed in a freezer that uses CF2Cl2 as a refrigerant. The heat of vaporization of CF2Cl2 is 158 joules per gram. What mass of CF2Cl2 must be vaporized in the refrigeration cycle to convert all the water at 22 degrees Celsius to ice at negative 5 degrees Celsius? The heat capacities of water, solid, and liquid are provided respectively, and the enthalpy of fusion for ice is again provided. So the mass of the water, right, is going to be equal to the 18 ice cubes, right? And since 30 grams per ice cube, right, 30 grams of water per ice cube, well, we can easily multiply that to find the total mass of the water. And if you notice, we're going from water in the liquid state, 22 degrees Celsius in the liquid state, to water in the solid state at 0 degrees Celsius. And then, of course, we have this phase transition from 0 degrees Celsius to solid at 0 degrees Celsius. And then finally, from solid at 0 degrees Celsius to solid at negative 5 degrees Celsius. So we should calculate all of that heat energy that will be released. And of course, these all will be negative values. But where CF2Cl2 comes in is that the heat lost by the water is equal to negative heat gained by the surroundings, right? And CF2Cl2 is part of the surroundings. And so, of course, Q lost is a negative value. Q gain, therefore, is a positive value, right? So, and what you can do is take that heat energy. Of course, it's the same thing as the Q loss, only it's a positive value since Q loss is equal to negative Q gain. And so that value then, right, you'll use the heat of vaporization of CF2Cl2. Of course, you should rearrange it such that you can, so since this will be in kilojoules, I'm going to put kilojoules in the denominator to 1 gram, right? And so essentially, this is how much kilojoules of energy is required to vaporize 1 gram of this substance. And so if I do this conversion, I can find the mass of CF2Cl2, the refrigerant that must be vaporized, right, in order to kind of absorb this heat from the water. In order to convert liquid water at 22 degrees Celsius, this mass of liquid water at 22 degrees Celsius, to that same mass of solid water at negative 5 degrees Celsius. Finally, we have, again, another similar problem, but we're given a 0.25 gram chunk of sodium metal is cautiously dropped into a mixture of 50 grams of water and 50 grams of ice, both at 0 degrees Celsius. The reaction is 2 moles of sodium plus 2 moles of water to yield 2 moles of sodium hydroxide and 1 mole of hydrogen gas, and the change in H associated with this equation is negative 368 kilojoules. And so that change in H is negative 368 kilojoules per 2 moles of sodium reacted, per 2 moles of water reacted, per 2 moles of sodium hydroxide produced, per 1 mole of hydrogen gas produced. So the question is, will the ice melt? Assuming the final mixture has a specific heat capacity of 4.18 joules per gram degree Celsius, calculate the final temperature. The enthalpy of fusion for ice is that. So here, again, you begin with the sodium metal, and we need to find, based upon this chemical process, how much heat energy would be released by this process. And of course, so we'd convert this to grams, and then using this enthalpy change associated with this reaction, negative 368 kilojoules per 2 moles of sodium, not per 1 mole, but 2 moles of sodium reacted. And that can give us the heat change from this system. And so that heat will be lost and absorbed into the surroundings, which is made of the water and the ice. But they're both at 0 degrees Celsius, so you should focus on the ice, whether that amount of heat energy, whether if it is absorbed by that system, by the ice, would that melt the ice? Of course, you should convert grams to moles and then use your heat of fusion to see if that would cause the solid to turn to liquid state. Till next time, Crip.